Question 9, Part B. A superannuation fund pays an interest rate of 8.75% per annum, which compounds annually. Stephanie decides to invest $5,000 in the fund at the beginning of each year, commencing on 1 January 2003. What will be the value of Stephanie's superannuation when she retires on 31 December 2023? This type of an investment is an annuity because it consists of a series of regular contributions made over a period of time, earning compound interest. So I'm going to model the annuity using a recurrence relation to find the value of the annuity at the end of the first, second, and third years, then use the sum of a geometric series formula to represent the pattern of the recurrence relation. So to make this process a little easier, I'm going to use algebra rather than using the values themselves. So I'm going to let capital M, I'm just going to say M at this point, so I'm going to let M equal 5,000, which represents the value of each contribution. Capital R is equal to 1.0875. Now I'm going to use capital R instead of little r, because capital R represents the factor by which I used to increase the previous year's value by 8.75%. And AN is equal to the value of the annuity after n years. So now to model this situation using a recurrence relation. So A naught is equal to M, and that's the value of the annuity initially, so no interest has been earned at this point. A1, so that's the value of the annuity after 1 year, is equal to A naught times capital R, and A naught is equal to M, so A1 is equal to M times capital R. A2, or the value after the second year, is equal to A1 plus M. So A1 is the value of the annuity after the first year, plus 1 contribution of M. And I'm going to put that in brackets, and then increase that by 8.75%, which is done by multiplying this expression here by capital R. Now A1 is just equal to M times capital R. So A2 is equal to M times capital R plus M in brackets times capital R. Expanding the brackets, we get A2 is equal to M times capital R squared plus M times capital R. Now A3, which is the value of the annuity at the end of the third year, is equal to A2 plus M in brackets times capital R. Now A2 is equal to M times capital R squared plus M times capital R. So A3 is equal to M times capital R squared plus M times capital R plus M in brackets multiplied by capital R. So again, we're going to increase this value by 8.75%. Expanding the brackets, we get A3 is equal to M times capital R cubed plus M times capital R squared plus M times capital R. Continuing the pattern to find an expression for AN, so that's the value of the annuity after n years, we get AN is equal to M times capital R to the power of n plus M times capital R to the power of n minus 1 plus M times capital R to the power of n minus 2 plus ... plus M times capital R squared plus M times capital R. And if we factorize out M times capital R from this expression here on the right hand side, we get AN is equal to M times capital R outside of 1 plus capital R squared plus ... plus capital R to the power of n minus 1. Now note that there are n terms in this series here in brackets. And this series also is a geometric progression. And we can model this series using the sum of a geometric progression formula. Now the first term is 1, and the common ratio is capital R, and there are n terms. So AN is equal to M times capital R times 1 minus capital R to the power of n over 1 minus capital R. Now from 1 January 2003 to 31 December 2023, we get n is equal to 21 years. So I'm going to substitute n equals 21 into the formula here. Now we have the value of capital R, which is 1.0875, and the value of M is 5,000. So A21 is equal to 5,000 times 1.0875 times 1 minus 1.0875 to the power of 21 over 1 minus 1.0875, which equals 299,604.8566. Therefore, the value of the annuity is $299,604.86.